Lab 4 about oscillations. So some key concepts are the force of gravity. We're going to be working near the Earth's surface, and so we're going to be using this acceleration due to gravity, which we're always pretty much using. Again, we're going to be thinking about Newton's second law, acceleration of an object, and this is essentially important to understanding the energy change in an object, which are heavily related to the momentum. Also, velocity update and position update are the same. These concepts are in pretty much every lab. Also, change in energy of the system equals the work done by the surroundings plus the exchange in thermal energy with the surroundings, which you can see here. We will be incorporating that. And basically, inside of that total energy of the system, you got the kinetic energy. Translational just means that, like, if objects hit each other or interact, then it changes. And basically, it's 1/2 mv squared, with this being the speed. And gravitational potential energy is minus because it's down. Mass, acceleration due to gravity, and basically the height. Spring potential energy is 1/2 ks squared. This is the spring constant, and s is the distance of the spring, like the extension, minus its resting length, basically. So the goals of the experiment are to compare the predicted motion of a spring in a pendulum with the observed motion. This will show comparative changes in energy. So the change in energy should be 0. So in our predicted motion in our model, we're going to set it to 0, as no external energy should be affecting the system. So we're going to need to assume minimal transfer of energy between the spring and the surroundings in order to simulate this. So here we go. No work done by the surroundings, no exchange of thermal energy. The delta E is 0. The free body diagram, we got the spring force. It's actually not always just in the y-axis. It's like going around in x-axis or even the z-axis if we incorporated that too. But the force of gravity is always just in the y-axis, and that's going to have the net force is going to be between these two forces, basically. So if we go to our tracker analysis, which I'm not going to show you because it just takes a while to look at the video, but you basically have an oscillation here, and then using these defined mass at spring constant and relaxed length values in conjunction with what we got from the tracker, which is the positions, which don't change very much, and that makes sense because the pendulum essentially moves like this. I'm moving my mouse. The initial velocity is 0 because it's dropped, but more importantly, you get the change in time, which is going to be important for some of our calculations. So in the computational model, the net force here, force of gravity plus force of spring, here it is written out. It looks scary, but it's really not too bad. And I believe you can see that in the code. Also, we're going to have to code for that S value. We're going to have to code for the energies, 1/2 mv squared, etc. And we're going to have to code for the change in energy equaling 0, and then equaling these added together. The force of gravity is only the y-axis, so it is minus mg, and the spring force is going to be that k distance, like difference in spring length, and then this just being the vector. Also, we're going to have the standard velocity and position update formulas in here. And here's all the code. So when we run this computational model, what we get here is these change in energy graphs, which essentially show that the total change in energy always stays 0, and that the kinetic energy is always opposing the difference, so that it's 0, right, between the potential energy of the spring and the potential gravitational energy. And as they oscillate, again, that delta E is always at 0. So how does it compare to our experiment? Here you can see the experiment is somewhat off. It's a little bit smaller, and it's also getting slower. And this is especially true with Y. It's getting smaller over time. And that's essentially because of drag. So change in gravitational potential energy and spring energy, you can see that they're always opposite in sign, and they're oscillating. You can see that right there. The change in kinetic energy also oscillates, and it's just much smaller, and that's just because it's not moving very much. But it has a lot of tension, still a lot of gravity, of course. The Y position graph experiment showing greater decay also just demonstrates that it's less accurate, maybe has more error. The model does not account for drag, and it also doesn't account for any thermal or rotational or any other kind of energy transfers. And there's also just some possible user error. So what does it mean? Is this energy principle satisfied? Yes. You can see here that it's always at 0, and because the graphs line up pretty accurately to our model, you can basically confidently say that the exchange in energies, the differences here between them added up, and this is just an example, are always at 0, which makes physical sense. Also, what does it mean? What are the oscillation periods? So finding the periods by averaging 3 different periods of time, You get 1.7 and 1.5, the difference being 1.23. And that difference is caused pretty much purely by error, drag, unaccounted energies, etc. I hope this was informative.